Thank you for the introduction. Afternoon, today I'll be presenting Themis, a system that schedules multiple deep learning workloads on a shared GPU cluster in a fair and efficient manner. This is joint work with collaborators from University of Wisconsin and Microsoft Research. Large enterprises are using deep learning for all sorts of tasks such as speech recognition, image classification, and so on. Individual teams in these enterprises constantly innovate and train newer deep neural network models, typically on hardware accelerators such as GPUs. Training typically involves hyperparameter optimization, which essentially requires training several copies of the same deep learning model with different parameters, which we refer to as a deep learning app. In this example, you see a deep learning app with 4 jobs training the same model with different learning rates. To highlight prevalence of deep learning apps, let's look at this graph which plots the CDF of number of jobs in deep learning apps from a trace obtained from a GPU cluster at Microsoft. We see that there are only about 5% apps with just a single job, and hyperparameter optimization with multiple jobs in a single deep learning app is the common case. As more and more teams require execution of these deep learning apps in their work pipeline, GPU deployments are changing. Instead of each team owning independent GPU instances, GPUs are being consolidated at large enterprises as a shared on-premise cluster or a cluster of cloud GPU instances. With this consolidation, a GPU cluster scheduler is required to multiplex access to these GPUs for deep learning apps from several teams. The key goal of the GPU cluster scheduler is to incentivize sharing of their own individual GPU resources. This can be formalized as sharing incentive, which is defined as if n deep learning apps are sharing a cluster, then no deep learning app should run slower than on a private cluster with 1 over n resources. In the rest of the talk, we first look at existing GPU cluster schedulers and their inability to provide the sharing incentive. We look at deep learning app properties, that is the root cause of these drawbacks in existing cluster schedulers, and motivate the key requirements for an ideal GPU cluster scheduler. In the second half of the talk, we'll look at Themis, which is a cluster scheduler we designed that gives the sharing incentive. There have been several proposals in the past. Of these, Slack, Optimus, and Gandiva have a different goal and do not directly address sharing incentive. DRF and Tiresias are fair schedulers that come close to providing sharing incentive. However, they have drawbacks as they do not account for properties unique to deep learning apps. We first look at DRF and its drawbacks. With DRF, apps interface with the scheduler and submit task resource demand. The DRF scheduler maintains the resource share metric per app, and as part of its mechanism, on any task completion event, allocates resource to app with the minimum resource share. DRF assumes short tasks to guarantee this sharing incentive, as this enables frequent task completion events and allows for frequent multiplexing of resources across all the contending apps. However, tasks in deep learning apps have a wide range of task durations. In this figure, we plot the CDF of task durations for apps. The median task duration is 3.75 hours, which is quite long, and there are a lot of tasks with 5x shorter and 5x longer tasks than the median. This can lead to long waiting times for shorter apps. Take the example of a short task from an app waiting behind a resource hogging long task from some other app. This causes long waiting time for the short app's task in this case. This means that short apps have no sharing incentive to share their resources with long apps. To overcome this issue, preemption of apps is a necessity. A way to enforce this is via the concept of leases, where any app's tasks are allocated resources for at most a lease duration at a time. With Tiresias, apps interface with the scheduler and submit their task resource demand. Tiresias maintains the attained service metric for each app. Attained service is the product of the number of GPUs allocated and the allocation time. Finally, Tiresias allocation mechanism allocates resource to the app with the least attained service for a least duration. However, Tiresias fails to accommodate placement preferences of these deep learning apps. This figure shows the training throughput in images per second with a dense placement of 4 P100 GPUs on a single server as red bars, and a sparse placement of 4 P100 GPUs spread across 2 servers evenly as blue bars. We see that VGG model family prefers a dense placement to a higher degree than AlexNet, and AlexNet prefers a dense placement to a higher degree than Inception and ResNet. Consider a sparse and a dense placement scenario as shown in the figure on the right. In both placements, the attained service metric is equal. Tiresias deems both placements as equivalent. This can lead to a bad placement for a VGG app with Tiresias and can lead to slower execution time for a placement-sensitive app. In this case, the VGG app would prefer an independent server for itself and has no sharing incentive. Tiresias proposes a binary placement enforcement optimization, which for highly placement-sensitive apps like VGG prefers waiting in a queue for dense placements. However, this fails to account for the fact that partial progress can still be made with a suboptimal placement. This leads to lost opportunities to make app progress, and this inability to account for fine-grained placement preference can lead to long wait times and hence sharing incentive violations. To overcome this issue, accounting for fine-grained placement preference of apps is important to guarantee sharing incentive. In the rest of the talk, I'll describe our proposed GPU cluster schedulers Themis in detail. With Themis, we achieve the goal of providing sharing incentive by proposing a new scheduler metric, reimagining the interfaces between the app and the scheduler, and proposing a new GPU allocation mechanism. The key contribution of Themis is a new metric that captures the sharing incentive. The interface design and the mechanism revolve around the choice of this metric. Before we look at the metric in Themis, let's look at sharing incentive through an example. Say the green app's finish time is TSH in a shared GPU cluster, and say the green app's finish time is TID in its own independent GPU cluster. The goal of sharing incentive is to enable better performance in a shared cluster. This means that TSH should be less than or equal to TID. Themis defines a new finish time fairness metric, rho, which is the ratio of the TSH to TID. Sharing incentive can then be formalized as rho less equal 1 for all the apps in the workload. This metric accounts for fine-grained placement preferences as excessive queuing or continuously bad placements worsens the value of TSH, the shared running time, and hence the value of rho. Now that we have a metric that captures sharing incentive, let's look at the interface between the app and the scheduler. The key purpose of the interface between app and scheduler is to aid the scheduler to maintain updated values of rho. The key question to answer in deciding the interface is who calculates the value of this rho? Is it the app or the scheduler? To answer this question, let's look at a typical deep learning app. An app is typically managed by a hyperparameter optimizer like Google Vizier or Hyperband or Hyperdrive. This hyperparameter optimizer launches several deep learning jobs with different hyperparameters. The hyperparameter optimizer's allocation logic decides split of the app's overall GPU allocation across the individual training jobs in the app. And the hyperparameter optimizer's termination logic tracks the training accuracies of each job in the app, and it classifies these jobs into categories such as poor, good, and okay. And Themis uses this information to estimate the finish time of each job, and hence the value of rho, which gets progressively accurate with app's execution. So in summary, in Themis, we leverage the per job progress information maintained by the hyperparameter optimizer, and punt the calculation of row to the app. Themis scheduler pulls these updated row values from the app's hyperparameter optimizer by using a Themis agent, which acts as a shim layer for enabling this interface. We refer you to the paper for the details of Themis agent for different hyperparameter optimizers like Hyperband, Hyperdrive, and Google Vizier. Now that the interface in Themis is decided, we look at the allocation mechanism in Themis. The key goal with Themis is to guarantee sharing incentive, which means for all apps, row is less than or equal to 1. However, this is difficult to guarantee in practice with online arrivals of apps where the contention over time changes. Instead, we focus on tracking the min-max row objective, and we find that empirically this keeps rows close to 1 without any admission control. Let's look at a strawman mechanism through an example. Say there are 2 servers and the red GPUs on one of the servers become available. First, the scheduler pulls row estimates from all the apps by using the app to cluster scheduler interface. The strawman mechanism sorts the apps in decreasing orders of row and allocates resources to the app with the highest row. In this case, it's the green app for a least amount of duration. There are 2 issues with this strawman. First, this can lead to inefficient allocations, as in this example, the red GPUs are not co-located on the same server as the green app's GPUs. Second, this incentivizes lying, as apps can lie with high row values to hoard GPU resources. Themis overcomes these issues and via a mechanism that operates in 2 steps. In the first step, we filter the top 1 minus f fraction of apps with max row values, and in the second step, we allocate available GPU resources, which are the red GPUs in this case, to one or more of these filtered apps using partial allocation auctions. The first step of filtering enables a trade-off between sharing incentive and efficiency. So as f tends to 0, more apps vie for GPU resources, and this provides better opportunity to match placement preferences of apps to the right subset of available resources. In this example, the red GPUs can go to the blue app, leading to a more efficient allocation. Our sensitivity analysis suggests that the value of f as 0.8 gives efficient allocations without affecting sharing incentive. The second step of partial allocation auctions is so as to incentivize truth telling of row from apps and enable an efficient matching of resources to apps within the filtered set. To elaborate on the auctions, a resource offer is made to the filtered apps, and each app makes a bid for these resources. The bid from each app is a valuation table as shown in the figure. For example, this valuation table has 3 rows. With no additional resource, the value of row remains unchanged. With 1 additional red GPU, the value of row, say, improves to row minus delta. And with 2 additional red GPUs, the value of row further improves to, say, row minus 2 delta. Now, the goal of the auction is to take these valuation tables from all the apps and allocate GPUs so as to maximize the collective valuation, that is, maximize product of 1 over rows for all the participating apps. To do so, we compute proportional fair allocation, and this guarantees Pareto efficiency. Further, to incentivize truth telling, we allocate only a fraction of this proportional fair allocation to each app. The rest is retained as a hidden payment. Intuitively, this hidden payment is designed such that more lying leads to higher hidden payments, and thus this incentivizes truth telling and guarantees strategy proofness. The hidden payments are allocated to the unfiltered apps, the apps that did not take part in the auction, at random for work conservation. We refer you to the paper for additional details and proofs. In summary, Themis proposes a new finish time fair metric that captures sharing incentive. Themis proposes new interfaces between the scheduler at the bottom and the hyperparameter optimizer at the top, via a Themis agent. And Themis proposes a new mechanism that gives sharing incentive, Pareto efficiency, and strategy proofness. For our implementation, we use 3.2.0 branch of Hadoop, which has Submarine, which enables launching of deep learning jobs. We implement the cross-app GPU cluster scheduler in Hadoop Yarn Resource Manager and implement the per-app hyperparameter optimizer and the per-app Themis agent in the Submarine application master. For our evaluations, we use a 20-machine 64 GPU testbed, and we use a publicly available trace of deep learning apps obtained from a GPU cluster at Microsoft. For our baselines, we compare against Tiresias, Optimus, Gandiva, and Slack. We first look at sharing incentive. For this, we plot the CDF of finish time fairness metric for all the apps in the workload across different schedulers. One, we observe that the distribution of rows for Themis is tight and most row values are around 1. The max row value with Themis is 1.2, and this is without any admission control. With other schedulers, we see a longer tail for row values, as some schedulers do not account for placement sensitivity, and some schedulers do not focus on sharing incentive goal. We next look at efficiency. For efficiency, we plot GPU hours used to complete execution of the workload for different schedulers. We observe that Themis is more efficient and uses least number of GPU hours due to more efficient packing of placement-sensitive tasks. Themis does better than greedy packing heuristics in Gandiva due to the auctions, in which in Themis enables global optimal packing decisions. We next look at the trade-off between sharing incentive and efficiency as we vary the value of fairness knob from 0 to 1. The figure on the top plots the max value of row across all the apps in the workload on the y-axis versus fairness knob values on the x-axis. Lower max row values are preferable and means better sharing incentive. The figure on the bottom plots the GPU time to complete execution of the workloads on the y-axis versus different fairness knob values on the x-axis. Lower GPU time is preferred and means better efficiency. As we increase the fairness knob value, each resource has fewer app choices to be allocated to. In the graph at the bottom, we see that up to a fairness knob value of 0.8, efficiency does not worsen, as there are sufficient choices to pack better. Beyond 0.8, efficiency takes a hit. In the graph at the top, we see that the sharing incentive gets worse as we increase fairness knob beyond 0.8. This is because we observe suboptimal placement as fewer apps enter the auction, which leads to degradation of row value. In summary, we see that value of fairness knob as 0.8 maximizes sharing incentive without degrading efficiency. In conclusion, we saw that to aid consolidation of GPUs into shared clusters, guaranteeing sharing incentive is key. We saw that existing schedulers violate sharing incentive because they do not account for properties unique to deep learning apps. We proposed a new finish time fairness metric that captures the sharing incentive and proposed a filtering plus partial allocation auction mechanism that gives better sharing incentive and efficiency than existing schedulers. Thank you, and I'm happy to take any questions.
Question for Kshiteej?
Hi, Jeremy Epstein, National Science Foundation. Old timer, thinking back to history. When we used to have time-sharing systems back in the 70s, we worried about a lot of these problems in scheduling different kinds of programs that had different needs. How much of this is reinventing some of those scheduling problems, and how much of it is fundamentally different?
One, I was not born in the 70s.
I recognize that.
But
I recognize that, but we worried about large computers that were running very compute-intensive jobs and very interactive jobs at the same time, and we needed to figure out how to schedule them efficiently. And it seems to me that what you have is very much the same. You have very compute-intensive things like the machine learning applications, and you have much more short-term things. And we figured out some of the pros and cons of different scheduling algorithms, and I wonder whether we can learn from history.
Yeah. I think the main deep learning apps are typically long-running, have long-running tasks. So that's why we have this notion of finish time fairness, where we're tracking the eventual end time, and you can take away scheduling opportunities for long apps and give it to shorter apps. I think in principle this must have been done in the 70s too, probably.
Right, that's the reason Unix scheduling worked the way it did back then, is specifically to allow that.
Yeah, but I don't know if hardware accelerators, as GPUs, GPUs cannot be multiplexed across multiple apps at the same time.
Right.
You have to allocate it to one job at a time for sufficient duration.
Right.
You cannot frequently deallocate and allocate jobs on a GPU. So that is different from, say, CPU land.
Okay, might be worth thinking about history a little bit.
Okay, let's thank our speaker again.